Now, of course, we have to look at a few angles in equilibrium. One is to discuss your understanding with what is actually equilibria and what you understand about reversible equation. Part two will be definition of acid base and how are you going to decide whether that acid base is strong or is a weak base or is a strong base or the vice versa. And part three, we'll be discussing about dissociation constant, okay, which is Ka, dissociation constant for acid, dissociation constant for base, Kb, and we also will discuss about solubility product, which is Ksp. Yeah, so that will be the third part. For the first part, okay, this is the learning objective. Okay, I hope that you can see. Okay, so after completing this topic, okay, after completing this topic, at least we have the basic ideas of what is chemical equilibrium, okay, what an equilibrium constant is, okay, definition or what do we understand about equilibrium constant, okay, what is the meaning, and when the value is, when we have calculated certain value, what does it mean, what the equilibrium constant value means to that reaction, okay, what does it mean, reaction quotient, okay, all right, we will discuss what it is. Use equilibrium constant to describe systems at equilibriums. Again, discussing the equilibrium constant. Recognize the factors that affect equilibria. Definitely, this is very important to recognize what are the factors so that we can manipulate or control the equilibrium and predict the resulting effects. So once we manipulate or change, then we can try to predict what will be the result. Explain the significance of equilibrium constant, okay, which is Kc, okay, to Kp when we have gas, when we have gas reaction, because Kp is related to pressure of gas. So when we have gaseous system, we don't really calculate the concentration in normal manner, just like solution, but we calculate using the pressure of the gas. Describe heterogeneous and homogeneous equilibria and write their equilibrium constant. So this is a learning objective for the first part of chemical equilibrium. So the first thing that we have to understand that when a system is referring to a chemical reaction, yeah? the forward and the reverse reaction rate. Yeah, remember, usually we have a confusion that when system at equilibrium, the forward and reverse reaction is the same. It's not the forward and reverse reaction is the same, it's the forward and reverse reaction rate is the same. Okay, so you have to be careful. The forward and reverse reaction are proceeding at the same rate. So the rate of forward and reverse reaction is the same during equilibrium. So when you say system is at equilibrium, if the reaction, the forward reaction and the reverse reaction is the same, is wrong. Okay, so please remember that. So another characteristic during equilibrium is the concentration of all species. Okay, concentration of all species remain constant over time. Okay, but both the forward and reverse reaction never cease. Okay, so equilibrium is signified with double arrow, means that you have reversible reaction. So what you need to pick up from here is the definition of what is equilibrium, a system at equilibrium, and the concentration of all species remain constant over time. Okay, so you have to understand that first. And if you look at in terms of graph, we are using an example, decomposition of N2O4 into NO2. Now, if you look at this, y-axis is concentration. Okay, so you can see at the beginning, the concentration of the reactant, of course, is the highest, and the concentration of the product is at 0 because nothing yet being converted to NO2. So you can see as time proceeds, as time goes, okay, right? You can see that the concentration of N2O4, which is the reactant, going down, the concentration going down, and the concentration of the product, which is NO2, going up. And they achieve, you can see, constant. Okay, they are now constant, right? It's not the same, but it is constant. The concentration of reactant now remain constant at one level, okay, at certain concentration, and the concentration of product now remain the same at one fixed concentration. And this is what we call as equilibrium, okay? Means that the rates of forward reaction and backward reaction is now the same. So the ratio of the concentration of reactants and product will remain the same. So if you interfere, let's say if you interfere with the system, you add some product or you add some additional reactant, additional product from outside, the system will move. The system will move to come back to this situation, to come back to the equilibrium. So that's what happened. We will discuss it later. Means any external factors, you add additional, or you put pressure, you put temperature, so there will direction, the system will rearrange itself so that it will go back to the original equilibriums that it has achieved. Okay, so you have to be able to draw this diagram. Let's say if you are asked to answer the question, what is equilibrium? Okay, when you try to define what is system at equilibrium. So there is a okay, so this is just a picture, a diagram showing that the N2O4 okay, from here decomposition into NO2. So you can see that when it is achieved equilibrium, this is based on color, then you have the rate of forward reaction and the rate of backward reaction is the same, but their concentration is not the same. Okay, so you can have a look back at the graph. Okay, so how do we put it into mathematical equation? So do not be confused with kinetic, because if you remember kinetic, okay, let's say you have A plus B forming C plus D, okay. In terms of kinetic, we discussed that K, which is kinetic constant. There are so many K, okay, and then, okay, X, Y, for example, okay. And this expression has to be determined through experiment. Okay, we cannot say X is 1, Y is 1 because, based on the coefficient, okay, from the balance equation. Okay, stoichiometric coefficient. We cannot say, okay, X is 1 or Y is 1. We are focusing on reactant only, and we are talking X and Y has to be determined via experiment. And of course, there's one way of using a reaction mechanism. Okay, so even though that is not very correct, reaction mechanism. So in equilibrium constant, let me delete this first. So equilibrium constant, let's say you have this reversible reaction. Okay, let's say you have this reversible reaction, and you can see that D and E is reactant. Let's say if you are talking about forward reaction, and F and G is the product. We are talking about forward reaction. Since this is a reversible reaction, okay, then you might have a reverse reaction. So when it is a reverse reaction, you have F and G as the reactant and D and E as the product. Okay, so remember that, it can be that way. And the other difference between this expression of Kc, okay, equilibrium constant Kc, is we can use the exponent. The exponent in the mass action are the same as stoichiometric coefficients. Okay, you can see that F here is the stoichiometric coefficient of the reaction. Okay, same goes with others. G is the coefficient, D here, and so on. Okay, same goes with E. Okay, so Kc for the forward reaction, okay, is product, concentration of product. Okay, you can see that product G, F and G, concentration of reactant. Okay, so if it is for reverse reaction, you can name it as negative, and now D in E will be the product, F and G will be the reactant. Okay, and the power will be similar to the coefficient. So I'm sure that you have come across this. So it's not something out of this world. This is something that you have gone through. Let's say we have this reaction. Formation of hydrogen iodide from hydrogen and iodine. We can also say that it can be degradation of hydrogen iodide into hydrogen and iodine, because we use it during this example is also being used during kinetic. Okay, so equilibrium constant can be written in this way. So 2, because of the coefficient, stoichiometric coefficient, and Kc can be expressed like product, concentration of product over concentration of reactant. Okay, and why do we have at certain temperature? Because Kc, okay, Kc is affected by temperature. Okay, so remember that, okay, if you add in concentration, different concentration of hydrogen iodide, hydrogen or iodine into the system, they will rearrange itself. The Kc will be similar. But if you change the temperature, now the Kc will be different. Okay, that's why we have to write this. The value of Kc will be different at different temperature. Okay. Okay, so these are the characteristic of Kc, equilibrium constant. Okay, constant at a given temperature means that if you are doing the experiment at same temperature, then the Kc, the equilibrium constant should be similar. Of course, it will change if the temperature change, and does not depend on the initial concentration. So if you use initial concentration, a different initial concentration, you will achieve same Kc unless you use different temperature. So if Kc is more than 1 at equilibrium, means that products is more than reactant. Okay? Most reactants will be converted into product. So now, is the Kc more than 1 or less than 1? Yes?
More than one.
Okay, if you look at here, if Kc more than 1 at equilibrium, products will be more than reactant. So if you look back, is the product concentration more than reactant? Which one is the reactant? Which one is the product?
NO2 is product.
Yeah, NO2 is the product and 2O4 is the reactant. So now the concentration at equilibrium, which one is greater, reactant or product?
Product.
Reactant.
Reactant kan? Okay.
Reactant.
Alright, N2O4 concentration is greater than NO2, right? At equilibrium. Yeah, at equilibrium. Of course, initial it is more because reactant is supposed to be more than product. It has not been converted, yeah. So what does Kc should be greater or less than 1?
Less.
Yeah, okay. If you think that why, okay, you try to write it back. Okay, now it's product over reactant, right? So if product is less than reactant, of course you will get Kc less than 1. Okay, so if Kc is small at equilibrium, reactant is greater than the product, most reactant remain unreacted. Okay, so that is okay, so that another example. Okay, this is a simple example. If 0.035 mole of N2O4 is placed in a 1 liter flask at equilibrium, at equilibrium, okay, you achieve this, N2O4 0.0292 mole per liter, and NO2 at equilibrium is 0.0116. So you can calculate Kc by dividing product over reactant at equilibrium. Remember, this is initial. Okay, remember this is initial. And when we are discussing Kc, we are discussing concentration at equilibrium. Remember that. Equilibrium. Okay. So do not get confused. If you are given initial concentration, you have to calculate concentration at equilibrium in order to identify Kc. Okay, now this is mathematical operational that you can do. Remember that when we are discussing kinetic, we are identifying reaction order, okay, which is related to the tutorial last week. Reaction order using reaction mechanism, we can add, okay, the equation. Okay, we can add the equation, we can minus the equation. So same goes to on equilibrium expression. So if you look at here, equilibrium expression, you can do the reverse reaction. Okay, so it is not negative Kc, it's 1 over Kc. Okay. You can reverse the reaction and then you can multiply the coefficients by factors. Okay, so you can do mathematical operations. You can do mathematical operations towards the equilibrium expression. So this is equilibrium expression. Yeah, do not forget. So Kc is equilibrium constant, but the whole thing, which is here from here, is equilibrium expression. Just like, okay, if you remember rate law expression, so the whole expression is the rate law expression. So this is equilibrium expression. So you can do mathematical operations for the rate law expression. Okay, so this is an example. If you you have two equilibrium expression, okay, you have two, and let's say you plus this one, okay, you add this one, so the Kc will be times, okay, the equilibrium expression is times, okay. And then from here, let's say when you add the reaction, you can see that 2 nitrogen remain. Okay, it is there when you add these two. Oxygen now you have 4 O2 here plus these 3 O2. Okay, now if you have at the right side, okay, which is the product, and the second equation you have the same compound, but at the reactant side or the left side, you can cancel out. I hope that you know this. And then this one remain because you cannot cancel out. So this is the final equation when you add these two equations, but the equilibrium expression is Kc times Kc1 times Kc2. Yeah, you don't add up the value of Kc, but you times the Kc. Okay, so this is example of mathematical expression. So let's say if you minus, what happened? If you minus the reaction, what happens? Divide, yes, right, good. Okay, so that will be equilibrium constant. So another term that you should know is reaction quotient, Q. Okay, so Q, okay, has the same form as equilibrium constant. You can see that it has the same form, but it does not measure the equilibrium. They are not at equilibrium yet. Reaction quotient measure the progress. Okay, so how are you going to understand that is, okay, let me clean up first. Okay. So Q is the progress of the reaction until equilibrium is achieved. So whenever that you express the product of reactant, okay, before the equilibrium is achieved, okay, it is called reaction quotient. Okay, but once you achieve this equilibrium, now it is called Kc. So Kc is where at this level Q now is similar to Kc. Okay, but before equilibrium, Q is just a measure of progress. Okay, progress of the reaction. So how to calculate is the similar, it has a similar way of to express Kc. So do not get confused because you use the same expression. Q is also product over reactant, concentration of product over reactant. But once it is at equilibrium, now Q is Kc. So Q is how to measure the reaction progress. Yeah. So why do we need to measure the progress? Okay, because we need to know, let's say, because the equilibrium, okay, can be speed up. Okay, the process to achieve equilibrium can be speed up or can be slowed down. Okay, and then that's why we need to know Q. So if we know the Q, the progress of the reaction, we can know what are the strategy that we need to do Do we need to add some more reactant, or do we need to add some more product so that the process of achieving equilibrium will be faster, or whatever that you wish to be delayed or to be faster. So that's why Q is important as well. Okay. Okay, this is an example of calculating Kc, equilibrium constant. So I'm sure that you are very familiar with this table. Yeah. So this is initial. Okay. And this is concentration, the change of concentration. And this is equilibrium, yeah, concentration at equilibrium. So if you look at the questions, ethyl acetate is produced from acetic acid and ethanol by the reaction. Okay, which one is acetic acid? Which one is ethyl acetate? Okay, because it is given. So this is ethyl acetate produced from acetic acid and ethanol, okay, forming ethyl acetate, which is ester, and water. So at 25 degrees, okay, Kc is given to you for this reaction. Now suppose 0.1 mole of ethyl acetate and 0.15 mole of water are placed in a 1 liter reaction vessel. What are the concentrations of all species at equilibrium? So now you are having an external factor. External factor. Okay. So this is the original reaction. Okay. Not to say external factor, but this is a different. If you look at this, and why we are supposed to evaluate 0.1 mole ethyl acetate, but what we are looking at is the reaction of acetic acid with ethanol forming ethyl acetate, but given to you is 0.1 mole ethyl acetate and 0.15 mole of water. So now we know that this is a reversible reaction. Okay. So now ethyl acetate becomes the reactant. Same goes to the water. So acetic acid, and ethanol becomes the product. So that's why you can use this table, okay, because you wish to remain the value of Kc, okay, because Kc given to you is the forward reaction. It's not on the reverse reaction, okay. So that's why if you look at the table, we are still maintaining the forward reaction, okay. So at the beginning, no product, because now the product is acetic acid and ethanol. So at the beginning, you have 0.1 mole of ethyl acetate and 0.15 mole of H2O, right? And this one, I'm sure that you know, after the reaction, okay, there is a concentration change. X mole of ethyl acetate being used, as well as X mole of water being used and converted into X mole of ethanol and X mole of acetic acid. Okay. Since the reaction is quite easy, it's 1-to-1 ratio, everything is 1-to-1 ratio, so it's quite easy for you to put all in the form of X, X, X. So at equilibrium, you know the difference, the remaining, yeah, the remaining mole of ethyl acetate is 0.1 minus 8 minus X, and for water is 0.15 minus X. So this one is just X because there's no other sources of formation of acid acetic as well as ethanol. So the expression of Kc, because it is a forward reaction, okay, is product over reactant. In this case, because Kc, we still consider as ethyl acetate is the product, H2O is the product. So we put all this, everything, and you have to solve the quadratic equation. So I will not be teaching you on how to solve the quadratic equation. So this you should know from your mathematical knowledge. So in the end, you can solve the concentration at equilibrium for all the species involved. Okay, because once you know X, then you know all the concentration of all the species at equilibrium. Okay, question for this. Let me turn on. Okay, look at the question. So no comments, so everything is okay, yeah? Now it's very warm. I have to turn on additional. All right, okay. So this table, even though I know that some of you can just calculate the values in your head, you don't need this table. But whenever that you answer questions, okay, this table is very important because you'll be given marks. So make sure that when you answer question, please do write this table. Yeah, initial, the concentration change, and concentration at equilibrium. Yeah, and remember that it is not always a single X. Yeah, let's say you have, okay. It is not, the stoichiometric coefficient is not 1, then make sure that you should also have the coefficient here. For example, 2 or 3 here. Okay, I do not want to confuse you. Please remove this one. Yeah. All right, so this is the simplest example, right? Okay, so we have discussed in terms of mathematics on how you can calculate the concentration at equilibrium. Okay, the simplest one. So there are a few factors. Okay, there are a few factors that can affect the equilibrium constant, especially the equilibrium constant. Okay, so according to Le Chatelier, this is French, Le Chatelier's principle. If an outside influence upset an equilibrium, the system undergoes a change in the direction that counteracts the disturbing influence, and if possible, return the system to equilibrium. So we love equilibrium. So we love to be at stable condition. And we love status quo. So I don't know whether you know what is the meaning of status quo. Status quo is what is the original that we are at. Okay, so the system, the reaction loves to be at the original equilibrium. So let's say we add stresses, okay, external factors to that chemical reaction. For example, either we remove or we add product or reactant. You know that they have reversible reaction. So let's say we pick up some of the reactants, or we take it out the product. So what happened to the reaction? Okay, so the equilibrium shifts to remove reactant or product that have been added. The equilibrium shifts to replace reactant or product that have been removed. So how do we say this when we interfere with the concentration of product or concentration of the reactant? So according to the Le-Chatelier principle, the equilibrium, okay, the equilibrium will shift to the right or to the left. The equilibrium will shift to forward or to the reverse. Okay, means that it will quickly try to remove the reactant that you add, or it will quickly produce to replace the product that we add to the system, okay, that we have taken from the system. Okay, so the equilibrium will be shifted. Okay, the word is very important. Equilibrium will be shifted to the left or to the right, depends on the situation. Okay, okay, let's say, okay, now if you look at this reaction, okay, now I'm talking about the forward reaction, yeah, okay. Let's say I put it more ethanol into the system. So what happened to the shifting of the equilibrium? Will it shifted to the right or to the left?
Right.
Okay. Okay. So the answer is correct, but it has to be detailed. Okay. When I say, okay, let's say the first condition is I add more ethanol to the system. Let's say. So the answer is, of course, according to Le-Chatelier's principle, okay, the equilibrium will be shifted to the right and more ethyl acetate will be produced. Means that more product will be produced. Okay, so your answer is correct, but you should have more detail to that answer. Okay, let's say in another situation, I take out H2O from the system. I just scoop it out. So now what happened to the equilibrium shift? Yes? Yes?
Shift to the left and ethyl acetate will less produce.
Okay, and now I'm taking out H2O. So H2O is product or reactant in this case? I take out. It's not that I add.
Product.
It's the product, right? I take out. Okay. So I take out the H2O. Now what happened to the equilibrium? Okay, will the equilibrium, will the reaction producing more H2O or will be producing more reactant?
More H2O.
Yes, so the equilibrium will be shifted to the right or to the left?
To the right.
To the right, yes.
Right.
Because I remove the H2O. So the system will try to recover back. Okay, quickly recover. We have to recover. Somebody take our H2O. So the system will be shifted to the right so that more H2O, okay, more product will be produced. Of course, ethyl acetate also will be produced. Okay, but H2O has to be at the right side. So, okay. So that's why you have to sometimes the question will give you scenarios. Okay, what happened? Okay, and what happened to the reactant? What happened to the product? So whether the the equilibrium will be shifted to the left, so that more reactant will be produced, or the equilibrium will be shifted to the right, so that more product will be produced to recover back what has been interfered. Yeah. So that will be on the adding or removing. Okay. Okay. It might be changing the volume. Okay. Especially, okay, this one, of course, involve gases reaction. Okay. Reducing the volume of gases reaction causes the reaction to decrease the number of molecule of gas. So when we talk about gas, the concentration is related to pressure. So if we increase the volume, the pressure will go down, means the concentration now is getting less. Okay, so same way of how we deal with the first, which is when we add or remove the product. So now we are talking about the concentration, but of course volume is related to pressure, and pressure usually we talk about gas. Okay, so remember it's about gas, and it has negligible effect on reaction involving liquids or solids, usually. So changing the temperature. Okay, now we must remember that this is the only factor that can change the value of Kc. Okay, because if you try to change the concentration, the equilibrium will be shifted. Okay, and if we calculate back the Kc will be the same. But if we change the temperature, okay, what happened is we have to know about the reaction, whether it's endothermic or exothermic first. We cannot just decide based on what we have done before. Okay, so I'll be giving you an example. Okay, right. Okay, let's talk about the effect of temperature. Okay, A plus B, okay, C plus D. Okay, so let's say the forward reaction is exothermic. Okay, so now let's say I heat the reaction. So T now is increasing. I heat the reaction. So the system will try to lower down the temperature. Okay. Of course, I mean, this is something logical. I heat the reaction, the system will try to lower down because they want to retain the original condition. Now, if the forward reaction is exothermic, you know that the forward reaction will produce more heat because it is exothermic, right? So my question is whether the equilibrium will be shifted to the left or to the right.
To the right.
Any other answer?
Left.
Okay, why left, why right? Why left? Yes?
Since we want to lower down the forward reaction, I mean,
We want to lower down the temperature, right?
yes.
Because we heat up the reaction, we want to lower down the temperature. So we need to reduce the forward reaction because the forward reaction will give more heat, right? So we want the reverse reaction to be happening more, right? Because we know the reverse reaction will be endo, right? Okay. Do I need to repeat?
No.
Yeah, okay. So you're okay with this, yeah? So this is very important, okay? When you are deciding whether the equilibrium will be shifted to the right or will be shifted to the left based on the whether you are heating the reaction or you reduce the heat of the reaction. You cannot just decide, but you have to look at the original exothermic or endothermic condition. All right. Now, the next factor is catalyst. So it will not have the effect on the equilibrium position. It's just increase the speed on how fast the system will achieve equilibrium. Okay, so will not, the equilibrium will be there. The value of Kc will be the same, but you will, the reaction will achieve equilibrium faster if you have catalyst. And now if you add inert gases, for not necessarily a product or reactant. So if the added gas cannot react with any reactants or product, it is inert toward the substances in the equilibrium. No concentration changes occur, so Q still equals K and no shift in the equilibrium occur. But this one you have to be careful, because if the reaction involves gases, okay, if you add even inert gases, okay, there is a possibility that it increase pressure. And remember, pressure for gases is very important. But when you just add in inert gases, and considering the reaction is negligible, means that the gases is not really important in that reaction. So it is an inert gases, so it will not affect. But it will, if the reaction involve a lot of gases molecule, means that the mole of gases is significant, and then you add a lot of significant inert gases, then it will change the pressure. Okay, that is very important. You have to look at. So that's why we have the relation between Kc and Kp. Because for gases reaction, we don't really use Kc. Okay, so instead we have Kp in terms of pressure, partial pressure. Remember about the term partial pressure. Okay, total pressure and partial pressure for all the gases inside the container. And again, you can also relate PV equal to nRT, and this is something that you have to remember. Okay, the relation between Kp and Kc with RT and delta N. Delta N is the mole of gases of product minus mole of gases of reactants. Okay, so the relation between Kp and Kc is very important, yeah, for you to remember. Okay, this is just a description. Okay, what you can do when you have heterogeneous and homogeneous. Okay, if it is homogeneous, all reactants and product are in the same phase, mean that you are reacting gas with gas, liquid with liquids. But when you have heterogeneous, let's say you are reacting liquid and solid, or gases and liquid, so you have heterogeneous reaction. Okay, so it's just that heterogeneous reaction can also achieve equilibrium just like homogeneous system. So it's just that you should understand what's the difference between heterogeneous and homogeneous system. Okay, so I think we should take a break now. Do you have any issue with equilibrium part 1? Okay, the second hour we discussed about tutorial last week, which I have recorded but have not discussed with you. Okay, so the basic idea of chemical equilibrium. What is a chemical equilibrium, and how do you understand it in terms of graph, in terms of definition, the expression of equilibrium constant, how do you express, how do you write the Kc, and what is Q, what is the meaning of Q, and when is Q similar with Kc. All right, and then mathematical operations towards Kc, factors, okay, relation between Kc and Kp, and the last one, you understand what is heterogeneous and homogeneous chemical reaction, and it can also achieve equilibrium. Okay. All right, so we'll take a break. We come back at 3:10, maybe please have a look. For those who has not watched the videos, please look at it first, because I know I can track down how many watch it, or how many actually usually look at it. So please do look at it before we discuss it. All right. Okay, we gather back at 3:10. Yeah.